Good morning, students. I welcome you to the first session on phase rule. Today, we'll be discussing about what is Gibbs phase rule and what are types of equilibrium. Then, what are the various terms that we come across in Gibbs phase rule, their definition of the terms, and its explanation. Right. So, phase rule was given by American physicist Willard Gibbs. It was given by American physicist in the year 1874 by Willard Gibbs. And the importance of this phase rule is that this phase rule is flawless and has no limitations. Look at the beauty of this. Gibbs phase rule has no flaws and it has no limitations, unlike certain laws in real chemistry like distribution law, Ostwald's dilution law. These have certain limitations. Okay, but Gibbs phase rule is flawless as well as it has no limitations. And it is applicable to the study of all heterogeneous equilibria. So Gibbs phase rule is used in the study of heterogeneous equilibria. And this Gibbs phase rule helps us in predicting the effect of changing pressure or temperature or concentration. So Gibbs phase rule helps us, or the phase diagram which we construct. So phase diagrams help us in predicting the effect of changing temperature or pressure or concentration on heterogeneous equilibrium. Right? So Gibbs phase rule, it helps us in predicting the effect of changing the pressure, temperature or concentration on equilibrium. And this Gibbs phase rule, as I said, is applicable to heterogeneous equilibria. So what is meant by heterogeneous equilibria or heterogeneous equilibrium? So before going over to homogeneous and heterogeneous equilibrium, let us try to understand what is an equilibrium state. So equilibrium state of a system is the one in which there is no net change in properties of the system. So equilibrium state is the state of a system where there is no net change in properties of the system. For example, if you have water placed in a closed container. Okay, so in the beginning we have liquid water, and liquid water starts evaporating. So what happens? The water evaporates and gets collected within the container. It's a closed system. So after certain amount of water vapor is formed, it starts condensing. Initially there is only rate of evaporation. Then after some time condensation starts. And as the time goes on, an instant is reached where rate of condensation is equal to rate of evaporation. So that state in which rate of evaporation of water is equal to rate of condensation of water is called equilibrium state. So when liquid water is in equilibrium with its vapor water, means any property of water that you measure in this equilibrium state, it remains the same. Once in the beginning rate of evaporation is higher, so the quantity of liquid water is decreasing and the quantity of water in the vapor state is increasing. After some time rate of condensation starts. So what happens there also? Quantity of vapor water starts decreasing and a state is reached at which the rate of evaporation is equal to rate of condensation. So when rate of evaporation is equal to rate of condensation, the quantities of water in the vapor state and in the liquid state remains the same. and you measure any property of liquid water in the equilibrium state, there will be no change in the property with the time. So that is the meaning of equilibrium state. So equilibrium state of a system is the one in which there is no net change in the properties of the system, right? And this equilibrium is of two types, homogeneous and heterogeneous equilibrium. So what is meant by homogeneous and heterogeneous equilibrium? Homogeneous equilibrium is the one in which all the species are in the same physical state. Okay? And here, when the physical state of the system is different, when two different physical states are in equilibrium, then that type of equilibrium is called heterogeneous equilibrium. For example, you consider here liquid water is in equilibrium with the vapor water. So water in liquid state is in equilibrium with water in vapor state or gaseous state. So in this equilibrium, liquid water is present in equilibrium with the vapor water. So we have liquid state and gaseous state in equilibrium. Such type of equilibrium is called as heterogeneous equilibrium, because Gibbs phase rule is applicable to heterogeneous equilibrium. So what is heterogeneous equilibrium? When two or more different physical states are in equilibrium, then we call it as a heterogeneous equilibrium. When the physical state of the species present in equilibrium are different, then that type of equilibrium is called as a heterogeneous equilibrium. For example, if you consider sulfur, allotrope forms of sulfur, rhombic sulfur in equilibrium with monoclinic sulfur. This is a solid and this is also solid. So this type of equilibrium is called as a homogeneous equilibrium, right? Because the physical state of the species existing at the equilibrium is the same. So when physical state of the species in equilibrium are the same, then it's called as a homogeneous equilibrium. So that is so we learned what is meant by an equilibrium state, and also we learned what are different types of equilibria, namely homogeneous and heterogeneous equilibria. And Gibbs phase rule is applicable to heterogeneous equilibrium, and it helps us in predicting the effect of changing temperature, pressure or concentration on equilibrium state, right? And this Gibbs phase rule, there is no statement, we only write it at only mathematical form. Gibbs phase rule is given by the expression F is equal to C minus P plus 2. This is the mathematical statement of Gibbs phase rule. Or if you want to put it in a statement form, number of degrees of freedom is equal to the sum of components of plus 2 and minus number of phases. So we cannot, it is very difficult to put it in a statement form. Simply we say the mathematical form of Gibbs phase rule is F is equal to C minus P plus 2, where F stands for degree of freedom, C stands for number of components, P stands for phase, number of phases. 2 is a numerical, because 2 here indicates the two variables which are considered to construct phase diagram. Okay, so usually pressure and temperature are pressure and concentration, or temperature and concentration are considered as variables. Okay, so here the numerical 2 indicates the two variables, okay, which affect the equilibrium of a system. So F is degree of freedom, C is the number of components, P is the number of phases, and 2 is a numerical which indicates two variables which are used to draw phase diagram. And here you will be considering pressure and temperature as the two variables. Okay. So now let us try to define and try to understand what these different terms mean. So first one is phase, denoted by capital T. As a Gibbs phase rule is applicable to the study of heterogeneous equilibrium, and it is given by the form F is equal to C minus capital C, C minus P plus 2. So now we are trying to define and understand what is a phase. So phase is defined as a homogeneous, is defined as homogeneous and physically distinct part of a system bounded by a surface and mechanically separable from other parts of the system. Mechanically separable from other parts of the system. This is the definition of phase. It is whenever I consider phase, a phase is always a homogeneous one. So a homogeneous and physically distinct part of a system bounded by a surface and mechanically separable from other parts of the system. Okay, we are dealing with heterogeneous equilibrium where there will be two or more phases in equilibrium. So each phase that is in equilibrium should be a homogeneous phase and physically distinct from other parts. We should be able to distinguish that phase from other parts of the equilibrium and bounded by a surface. These are all the characteristics of the phase. Phase is a homogeneous one and physically distinct part bounded by a surface and mechanically separable from other parts of the system. We should be able to separate, not chemically, but by physical method. This is mechanically from other parts of the system. So this is the definition of a phase. So if we consider, when I say phase, homogeneous systems will have a single phase and heterogeneous systems will have two or more phases. For example, if you consider sugar solution, sugar dissolved in water. So this is a homogeneous system. There is a single phase. And what is a homogeneous system? The properties of system throughout will be the same. In a homogeneous system, in which are part of the homogeneous system, you measure any property, the property will have same magnitude. So if you take sugar solution, aqueous solution of sugar, it forms a homogeneous solution because sugar is soluble in water. So when you take aqueous sugar solution, it forms a homogeneous system. Why? There is only one phase. We do not see water and sugar separately unless it is a saturated solution. It's not saturated solution I am considering. So when I consider a sugar solution, it is an example of a homogeneous system because it's a single phase. And since it's a homogeneous, the properties of this sugar solution will be same throughout. Whether you measure the sweetness of water or sugar solution, each sip or each drop of this sugar solution from wherever you collect, it will have same taste, it will have same density, it will have same color. So it will have same properties. Wherever you measure any property of this sugar solution in the bulk, it will be the same. This is a homogeneous system. And if it is a saturated solution of sugar, what do you mean by saturated solution of sugar? Where there is an equilibrium between undissolved sugar and sugar solution. So this is sugar solution in equilibrium with solid sugar. This is a saturated solution. You keep on adding sugar to water, a fixed amount of water. A state is reached when no more sugar dissolves. Means some amount of sugar is left undissolved at a given temperature. So that undissolved sugar in equilibrium with the dissolved sugar solution constitutes what? Heterogeneous equilibrium. So you have this is a heterogeneous system. A solid sugar in equilibrium with the sugar dissolved in water. So it is a heterogeneous system, and we have two phases. One is a solution of sugar phase, the other one is solid sugar phase. One is a solution phase, the other one is a solid phase. So that's the meaning. And we can separate it. We can decant sugar solution, or we can filter sugar solution. So sugar syrup comes into the receiver flask, and sugar is left on filter paper. So it is possible to separate sugar from saturated sugar solution. So that's the meaning of a phase. Phase is a homogeneous and physically distinct part of a system, bounded by a surface and mechanically separable from other parts of the system. So that's the meaning of a phase. So when we consider saturated sugar solution, you have a aqueous phase and you have a solid phase, and both of them have the clear boundary of separation. As I said, this is solid sugar and this is sugar solution. So there is a boundary of separation between this solid sugar and solution. So this is one phase having this boundary, and this is the solid phase having another boundary. And the boundary of contact between two phases is called interface. The boundary of contact between two phases is called interface. Right? So now this is a homogeneous part, and this is also homogeneous. This is solid sugar and this is a sugar solution. So this phase is homogeneous. This phase is also homogeneous. So phase is a homogeneous and physically distinct part of a system, bounded by a surface and mechanically separable from other parts of the system. So this is one example of a system. This is one phase, the other phase. And if you take a mixture, a solution of two immiscible liquids like water and benzene. Water and benzene are immiscible, right? So you have a water layer here, you have a benzene layer, and there are two phases. This is water phase and this is benzene phase. Both are liquid phases, right? And this is the boundary of separation between benzene and water. So this is again another example for a phase. So you have a water phase and you have benzene phase. Both are physically distinct. You can see water layer and benzene layer. Benzene being less denser, top layer will be benzene layer, bottom layer will be water layer. So this is water phase and this is benzene, and both these phases have a distinct boundary of separation, and these two can be separated using a separating funnel. We can separate these two using a separating funnel. So that is the meaning of a phase. It's homogeneous and physically distinct part of a heterogeneous system. Again, you can say, I need not say that. Physically distinct part, homogeneous and physically distinct part of a system, bounded by surface and mechanically separable from other parts of the system. That is the phase. I think with this explanation, you should be able to have clear idea regarding what is meant by a phase. Right. Now, after discussing what is meant by phase, now let's discuss what is component, denoted by capital C. So components are number of components, we say. So number of components is defined as minimum number or least number, the least number or the minimum number of independent chemical constituents with the help of which the composition of each phase or every phase, the composition of each phase can be defined with the help of a chemical equation. So this is the definition. So number of components is defined as the least number or minimum number of independent chemical constituents needed to define the composition of each phase in the form of a chemical equation. Okay, so it's the minimum number of chemical constituents required to define the composition of every phase in the equilibrium in the form of a chemical equation. So that is the definition of a component or number of components. So for example, if I have ice in equilibrium with water, so this is solid state and this is a liquid state. They are in equilibrium and it's an example of heterogeneous equilibrium, right? So there are only two phases. One is solid phase of water, the other one is a liquid phase of water. So what is the number of components for this system? What is the number of components? Is the minimum number of chemical constituents needed to define the composition of every phase in the form of a chemical equation, right? So what is the composition of water? We represent the composition of water is H2O. So whether it is a solid phase or liquid phase of water, the composition is represented with the help of H2O. Or if you have water, liquid water in equilibrium with water vapor, this is another example, another type of equilibrium. So here composition of this phase is H2O, composition of this liquid phase or vapor phase also nothing but what? H2O. So the composition of these phases, each phase in these equilibria can be just stated in the form of H2O. So H2O is the only one constituent needed to define the composition of these phases. So whenever only one chemical constituent is sufficient to define the composition of every phase, then we call such a system as one component system. So when C is equal to 1, when C is 1, it is called as one component system, because in this system, in these equilibria, only H2O is sufficient to define the composition of every phase. So also if you consider sulfur, say rhombic sulfur in equilibrium with sulfur liquid. Let us see. So this is the equilibrium where rhombic sulfur, which is in solid state, is in equilibrium with liquid sulfur. So what is the composition of each phase? Whether it's in solid state or liquid state or gaseous state, sulfur composition is denoted by S. So all the phases of sulfur, solid phase, whether it's a rhombic sulfur or monoclinic sulfur, liquid phase of sulfur, vapor phase of sulfur, all these different phases of sulfur and their composition can be expressed in terms of only S. So it is again an example of a one component system. Now, if we consider aqueous sodium chloride system, aqueous sodium chloride solution. Aqueous sodium chloride solution. Again, it's a single phase system. Okay, unless it is a saturated sodium chloride where there are two phases. This is a homogeneous system. It's a single phase aqueous sodium chloride solution. So what is the composition of this aqueous sodium chloride solution? How do you say? What is concentration? I say it is 7% weight by weight. 7% by weight of sodium chloride. I say that it is a 7% weight. 7% by weight of sodium chloride. In the sense, 7 grams of sodium chloride in 100 grams of water. This is the composition. Okay, this is the concentration. So what is the composition of this? Concentration is different from composition, right? What is composition? What amount of each constituent is present? Okay, so composition is what? It can be represented in the form of what? Sodium chloride, X grams of sodium chloride and Y grams of water. This is the composition. So what is the composition? 7 grams of sodium chloride, 100 grams of water. This is the composition. Concentration is 7% by mass or weight, whereas composition is 7 grams of water plus 100 grams of water. Or in general, we can write it as X grams of sodium chloride or X moles of sodium chloride and Y moles of water. So this is the composition. So how many constituents are needed to define the composition of this? One is NaCl, the other one is H2O. So two components are needed to specify the composition of this sodium chloride solution. So here number of components is 2, so it's a 2-component system, right? Okay, we are able to represent this composition of this solution in the form of an equation. X moles of NaCl plus Y moles of water, or X grams of NaCl plus Y grams of water. So in the form of an equation, we are able to explain the composition of this phase. So this is a 2-component system. For example, if you consider this type of equilibrium, decomposition of calcium carbonate in a closed vessel, because this equilibrium is attained only in a closed vessel. If you heat calcium carbonate in an open vessel, carbon dioxide formed escapes and we never attain this equilibrium. So this equilibrium can be attained in a closed vessel. And how many phases are there? 3 phases. One is calcium carbonate solid phase, second one is calcium oxide solid phase, the third one is carbon dioxide gaseous phase. So there are 2 solid phases and 1 gaseous phase. Okay, so there are 3 phases which are in equilibrium. And what is the number of components in this case? What is the number of components? The minimum number of independent chemical constituents needed to specify the composition of each phase in the form of a chemical equation. So calcium, there are 3 phases: calcium carbonate phase, calcium oxide phase and carbon dioxide phase. And this calcium carbonate phase composition can be represented like this. Calcium carbonate phase can be represented with the help of 2 independent chemical constituents like CaO and CO2. Right. Similarly, calcium oxide composition phase can be written in the form of a chemical equation like this. Calcium carbonate minus carbon dioxide gives a calcium oxide. So composition of calcium oxide phase can be written with the help of these 2 components in the form of equation. And similarly, carbon dioxide phase, the composition of this carbon dioxide phase can be expressed with the help of this equation. So calcium carbonate minus calcium oxide gives carbon dioxide composition, right? So this is how the composition of each phase in the equilibrium for decomposition of calcium carbonate can be expressed only with the help of 2 constituents. So again, the decomposition of calcium carbonate and its equilibrium is an example of 2-component systems. So C is 2 for calcium carbonate equilibrium system, right? So that's the meaning of compositions. Components, I'm sorry. C stands for number of components. Then F stands for degree of freedom. degree of freedom. So what is degree of freedom? Denoted by capital F. So degree of freedom is again defined as the minimum number of independent variables like pressure, temperature and composition. Independent variables like or such as pressure, temperature or concentration needed to define the state of a system completely. To define the state of a system completely. This is the definition of what? Degree of freedom. So it's the minimum number of independent variables like pressure, temperature, concentration needed to define completely the state of a system. What is the state of a system? You learned in thermodynamics. State of a system is the one in which the properties of the system have definite values. Properties of the system have definite values. That's the meaning of state of a system. So state of a system is the one in which the properties of the system have definite values. So what is a degree of freedom? It is the minimum number of independent variables like pressure, temperature, concentration, etc. needed to define completely the state of a system. For example, if I take 1 mole of an ideal gas, 1 mole of an ideal gas in a container. I simply say 1 mole of ideal gas is present in a container. So what is the state of the system? What are its properties? What is the state of a system? What are the properties of this 1 mole of ideal gas? So in order to define the state of this 1 mole of an ideal gas, I should specify at least 2 variables. What are those 2 variables? I have to specify either pressure and temperature, or I have to specify pressure and volume, or I have to specify what volume and temperature. Unless you specify this for this 1 mole of an ideal gas enclosed in a cylinder, without these specifications, without these properties, you cannot just imagine what is the state of that gas, 1 mole of ideal gas, right? So these are the minimum number of variables. Either I require pressure and temperature, or pressure and volume, or volume and temperature to define the state of this gas. So here the degree of freedom for this system is 2. Degree of freedom is 2 because I need to specify 2 variables like pressure and temperature, or pressure and volume, or volume and temperature, so that I have a clear idea of what its state is. Because when we do any of these 2 components, when I say 1 mole of an ideal gas at 300 Kelvin and 1 atmospheric pressure, this is the state. I am able to specify what the properties of the gas are. So I have 1 mole of an ideal gas at a pressure of 1 atmosphere and at a temperature of 300 Kelvin. So this is the state. These are independent variables. Volume is dependent. Once I know P and T, I can calculate volume also, so that I have all the properties of the system known. Using PV is equal to nRT, I can calculate volume also. Volume is a dependent variable. Pressure and temperature are independent variables because volume of the gas depends upon pressure and temperature. So by specifying any 2 variables, like any one of these 3 sets of variables, I am able to define the state of a system completely. So for this system, F is 2. So when number of degrees of freedom is 2, we call it as bivariant system. So what's a bivariant system? A system for which degree of freedom is 2. Such a system is called bivariant system. And if we consider ice in equilibrium with water, ice in equilibrium with water. So when this equilibrium is possible, only at 0 degrees Celsius. This equilibrium is possible at 0 degree Celsius. So if I just mention temperature or pressure for this system, I will be able to explain the state of a system completely. So this here F is equal to 1 is a monovariant system. Only at a given at 1 atmospheric pressure, only at this temperature, it is this type of equilibrium exists. So this equilibrium always exists as fixed temperature. If you change the pressure, temperature changes. That's all. So either by defining pressure or mentioning the pressure or by mentioning the temperature, we can define state of this system. Okay. So here when F is 1, it is called as monovariant system. When F is 1, it is called monovariant system. And if we consider another equilibrium, I is in equilibrium with liquid water, in equilibrium with vapor water. All the three phases of water are in equilibrium. All the three phases are in equilibrium. And these three phases in equilibrium are possible only when temperature is 0.0075 degrees Celsius and the pressure is 4.38 millimeters of mercury. So this equilibrium is possible. Which equilibrium? The equilibrium in which all the three states of water are present is possible only at this temperature and at this pressure. If you change the temperature, one of these three phases will disappear. If you change the pressure, again one of the three phases will disappear. It becomes a two-phase system. Only at this temperature and at this pressure, all the three states of water would be in equilibrium. So when temperature and pressure are fixed for this type of equilibrium, I need not specify anything because I say all the three phases of water are in equilibrium. When I say that, it is known that these three phases of water would exist in equilibrium only at 0.0075 degrees Celsius and 4.38 millimeters of mercury pressure. So I need not specify either temperature or either pressure because temperature and pressure are fixed for this equilibrium. Only at a particular temperature and pressure, all these three phases of water are at equilibrium. Hence, I need not specify either pressure or temperature to define this state of equilibrium. Therefore, for this equilibrium, degrees of freedom is 0, then this is called as invariant system or non-variant system. So when degrees of freedom is 0, it is called invariant or non-variant system. I repeat, this equilibrium where all the three phases of water are in equilibrium, to define the state of this equilibrium, I need not mention either temperature or pressure, because it's fixed. If you change any one of these two, either pressure or temperature, one of the phases will disappear, only two phases will be in equilibrium. So I need not say anything. For this equilibrium, if I say this equilibrium, immediately I say that pressure is 4.58 millimeters of mercury and temperature is 0.0075 degrees Celsius. So this is an example of a system for which F is 0, and when F is 0, it's called invariant or non-variant system. So I should stop here and continue in the next session. Thank you.